if we talk now about contrast in our image, so when we say contrast, this gets back to what I touched on at the very beginning, that if we have, let's say, some normal tissue and something abnormal and we're trying to differentiate them, we want to see a different amount of signal amplitude between those two regions. Otherwise, we're not going to be able to tell them apart. We could have the highest spatial resolution image in the world. If the signal from the tumor is the same as the signal from the normal brain or liver or muscle or whatever it is, they're going to look identical. Okay? And the same thing, you know, again, would pertain in functional imaging. If the signal due to whatever effect you're looking for is the same as the normal parts of the sample, you're not going to be able to tell them apart. So if we look first simply at what's going on with our transverse magnetization. Sorry. And what we've already said is that if we look at different tissues, they will have different exponential decays representing what happens after we achieve this 90-degree rotation of the magnetization and we turn off the input energy, the RF, and watch things relax over time. There is going to be a different time course, even though ultimately, if we wait long enough, they're all going to asymptotically approach zero. Zero transverse magnetization. So during this period of time, what we have, if we think about the signal that is measured in our coil, that it is getting smaller because the transverse component magnetization, which is rotating around B0, is getting progressively smaller. Okay. During this period of time, if we have our little antenna over here, which has a fluctuating voltage, remember that free induction decay that I showed you right before we went to lunch? So at any point in time, we can choose to measure the amount of signal that's induced. And that might be, let's say, at this time. So at this point in time, we're going to take the amount of signal intensity that we have and simply write it down. We're going to record it. Eventually, we're going to put it into an image. This time, by convention, is referred to as TE, or the time to echo, or echo time. The origin of the term echo is something we'll get to a little bit later today in brief, and we'll talk about it more on Wednesday. But suffice it to say for now, TE is simply the point in time at which we choose to record the signal. Now remember that from the moment that we start generating this net transverse magnetization, the signal is there. The signal's always there. This is just the time at which we choose to measure it. On the other hand, we could choose to measure this signal, right, very early, at this point in time. Now, what would be the difference between choosing yellow and measuring the TE very early on, or choosing, whatever that is, brown, and measuring it a little bit later on? Okay, there's more contrast. Before we even get to contrast, there's less signal the longer we wait. So let's just be clear about that. Signal is declining. Transverse magnetization is declining. Less signal is induced in our receiver the longer the period of time that we wait. But on the other hand, the contrast between these two tissues is declining, is increasing over time. There's a much bigger difference between red and blue at this TE indicated in brown than there is at that TE indicated earlier on. Okay? So, and this contrast, we can say, is telling us about differences in the T2 of the tissues. So by varying the time TE, by varying when we measure the signal, we can generate images that have different amounts of contrast based on T2. Okay? Now, these two tissues that I'm showing you in red and blue have different T2s. That's why they look different. Now they also, it goes without saying, have different T1s. How does that T1 contribute to this difference in signal? Anyone?
Not as much, right?
Someone says not as much.
Because it's happening on at a slower rate of the decay.
Okay. Actually, not at all. All right? Because what's going on here? We start out with our magnetization, based on this example, at rest, right? So if my forearm here represents the longitudinal magnetization of the sample, let's say it's right, red and blue, two different tissues. We'll do it this way. So here it is. We turn on our RF to rotate this 90 degrees. And now we wait, right? And these lose transverse magnetization at different rates. Okay? Now, at what point in that process that I just described has T1 relaxation occurred? Well, it's occurring simultaneously with this transverse relaxation, but it has nothing to do with the amount of signal that we have. Okay? This process has nothing to do, it's true that the longitudinal magnetization is also relaxing or is regrowing during this time point, but we don't measure that. So when we measure the signal, the only thing we're measuring is the loss of transverse magnetization. And the fact that these two tissues have different T1s really has nothing to do with anything. What is it that determines the amount of transverse magnetization that we have to start with at time 0? What determines this? What about the tissue? What about it specifically? The number of protons, or the proton density. This is what we talked about earlier, that this represents simply the proton density, because that's the amount of longitudinal magnetization, which, assuming these are both equal volumes of tissue, is simply a function of the number of protons within each of those volumes of tissue. When we turn on our RF, we turn all of that longitudinal magnetization into transverse magnetization. At this point in time, before any of this relaxation has occurred, the only thing that determines how much stuff, how much signal we have, is the initial proton density. And then as we wait over time and choose when we're going to sample the signal, the contrast will vary based on the T2 difference in the tissue. So how is it possible for T1, right, most of you have heard of images that we call T1 weighted images. T1 certainly is important to contrast in an MR image, but based on everything we've talked about until now, how do we have a scenario where T1 is contributing something to the contrast of the image? I mean, the short answer is we don't. Right? In this system that I've set up, T1 does not contribute anything to the contrast in the image. Now, let's look for a second at, again, at what is going on with longitudinal magnetization during this period of time. It looks something like this. Right? Okay? So, at time 0, and these times are the same, we take all of our magnetization, put it in the transverse plane, so that there's a large amount of transverse magnetization, there's no longitudinal magnetization. Then, what happens is we wait, and during this waiting period, there is relaxation of that transverse magnetization. At some point, we're going to measure it. During that time, there is also regrowth of the longitudinal magnetization. And if we wait long enough, all of this is going to fully relax and put us back to the same place we were right before this point in time. In which case, if we do it again, we put this back in the transverse plane, and we are back exactly to the same place where we started. Is everyone clear what I'm getting at here? That if we repeat this, and the reality is that we need to repeat this and measure this sample multiple times to generate an image. From a single measurement like this, we'll never be able to generate enough information to generate a usable signal, let alone an image. But if we do what I said, that we take our longitudinal magnetization, put it in the transverse plane, we wait now as it relaxes and measure the signal at some time TE, and then while this is all going on, that longitudinal magnetization is also recovering. And if we wait long enough, everything catches up and it becomes fully relaxed. We're back where we started. If we do it again, we end up at exactly the same time point. And if we wait that same time TE, we measure the same contrast, the same signal difference. And this contrast is a function of whatever proton density differences are embedded in the sample, as well as the echo time, TE, but has nothing to do with the fact that these have a different T1. So there is, however, a way for us to bring out that difference in T1. Let's just set this up as a slightly different example. So if this is time, and this is the longitudinal magnetization. So we start out with our, right after our 90-degree angle of rotation based on that RF pulse, we start out with 0 amount of longitudinal magnetization. Right? And if we just think about what happens to that longitudinal magnetization, what happens over time? Right? It recovers over time. And we can put, let's say, 2 different example tissues in here. Now, we see that these are all recovering to the same point. That tells us what about these 2 tissues, by the way? They have the same proton density, right? They ultimately have the same amount of longitudinal magnetization when they're fully relaxed. Now, we said before that if we would, at the same time, and what I'm doing here is just in parallel, because this is on the same time scale, I'm going to show you below what's going on with transverse magnetization. Okay? So where are we at this point in time? Right? Exactly, we're at our max. So if we draw our 2 different tissues in here, we're going to have something like this and something like this. Okay? And we could choose to sample at some TE. And at that TE, we will generate some contrast, a different amount of signal from these 2 tissues. That is a function of the fact that they have different T2. Well, that's fine. Now let's change this. And at this point in time, that wasn't very good. At this point in time, we're going to start the process all over again. So unlike the previous example, we're not waiting until these things get all the way out here and recover all of their longitudinal magnetization. Notice, by the way, as I indicated earlier, that the relaxation of transverse magnetization is on a much shorter time scale than the recovery of longitudinal magnetization. So even though this is all gone, there's no more signal left to detect. Right? The transverse magnetization is fully relaxed. At this point in time, we still, right, this stuff is all gone, but they haven't completely recovered their longitudinal magnetization. Well, if we start again, which means that we're going to give a 90-degree RF pulse once more at this point in time, well, when we give that 90-degree RF pulse, the only thing that we are able to rotate with that 90-degree RF pulse is the component of magnetization that's parallel to B naught, that's in the longitudinal direction. That's what we have up here. So at this point in time, when we give our 90-degree RF pulse, this is what happens. And what that means is that at our new starting point, okay, we have this much signal from blue, maybe that's CSF, and we have more signal, not quite as much as over there, but a bit more from red. Now these two, of course, are going to relax with their same, or as well as I can approximate it, loss of transverse magnetization. Now in this case, if we choose the same TE, what happens? Well, now, first of all, if we compare the contrast here, the magnitude, the size of the difference in signal that we detect between blue and red in our first iteration is larger than it is at our second iteration. Okay? So we've actually changed the contrast in the tissue, and the amount of time that we've allowed this T2 relaxation to go on hasn't changed. What has changed is the fact that we gave this second 90-degree RF pulse earlier on has embedded this difference in the signal, which is a reflection of T1 relaxation, not T2 relaxation. So now, whereas the first time that we sampled this signal, everything was a function of T2, the second time it's a function of T1 and T2. If we would have taken this out much farther, right, the farther out we go, the smaller this difference, and the less difference due to these T1 relaxation differences would be embedded in the signal that we sample at TE. Any questions about this? So if I want to make my image more sensitive to T1, if I want to see the differences in the tissue that are a function of those two tissues having differences in T1, I want to take this time, and this time is called the TR, or the time to repeat or repetition time. I want to make my TR shorter. Right? If I make my TR progressively longer, then these things are going to get closer and closer together, and I will have less and less of a difference due to differences in T1 embedded in that signal. If, on the other hand, I'm not interested in those T1 differences, which might be the case, I will want to push this repetition time out as far as possible, which essentially suppresses this information from my image. Okay, at the same time, adjusting the TE really has no impact on the T1 information in the image. It modulates the T2 contrast in the image. So if we say that we want to make an image that is T1 weighted, and I'm sure, Smith, in the review book, there's probably a nice little table to memorize this. So if you want to make a T1 weighted image, how would you choose these two parameters? TR and TE.
Find the maximum difference in the...
Well, a T1 weighted image would be an image where we're maximizing contrast due to T1 and trying to make that the exclusive determinant of contrast in the image. So we want to maximize what we can see in terms of T1 differences and minimize contrast that might be a reflection of T2. So to bring out differences in T1 contrast, we would want to do what? We want to make our TR, right, short. And if we want to make an image, and if we want to minimize contrast due to T2 in this image, we would make this TE very short. In our T1, we want to minimize the T2 contrast in the image. Well, this is all one image. This is all one process, okay? So this is our starting point. In this example, right, if in this signal, let's not even talk about an image, when we measure this signal, if we want to make this signal show us maximal differences between these two tissues that are based on T1, we want to make this TR very short. Right? And at the same time, to make that image as exclusively a function of T1 differences as possible, we want to minimize anything that is occurring due to T2 relaxation. So we will make our TE as short as possible. Okay? Now, on the other hand, if you want to make an image where the contrast in that image is a function of T2 to the exclusion as much as is possible of T1, you'll do what? Well, you'll bring out T2 contrast by making the TE longer. Okay? And you will minimize T1 contrast by making the TR, sorry.
Longer.
Just testing. By making the TR longer. Okay? Now keep in mind that no matter what you do, T1 and T2 mechanisms are always embedded in the signal that you detect in these images. Only in this one example, where we gave a single RF, the first time around, starting from rest, and there essentially was no T1 relaxation behind that. That was the only case where we didn't have any T1 information at all in the image. And that's not a realistic, there will be cases where that might happen, we'll talk about later in the week, but in general, we'll operate under the assumption that we need to repeat this again and again and again and again. Therefore, there is always going to be some TR, and there is, as a result, always going to be some T1 information in the image. Okay? Any questions about this?
Is TE relative to TR, or is it?
What does that mean?
Like, so the time to echo is always, a certain time after the TR, or?
So the time to echo is when you choose to measure the signal. Mm-hmm. Okay? The TR, the repetition time, is when you choose to repeat the whole process. So the TE does have to occur before TR. Is that clear? You could never have TR occurring before TE. You would be defeating the purpose.
Yeah.
So basically the sequence is that we give our RF to generate signal. At some point during relaxation, we measure the signal. And then at some point after that, we repeat the whole thing. That point is TR.
I'm just wondering if, like, when you specify a TR into a machine, if that's, is it the time between?
Is it tied to the TE?
Yeah, is it sort of TE plus TR equals the time, or is it TR is the time between each?
TR is the time from repetition to repetition. TE is the time from the initiation of one repetition until the time at which you measure the signal. They're otherwise, they're not related to each other. You're not restricted from, shortening or lengthening your TE or your TR, other than the fact that your TR really can't be shorter than your TE. Is that clear? Okay. So in this example down here, let's put this on another. Let's just point out one thing. Okay, so this is the example we just looked at, where the TR was relatively short. This difference, this is going to be determined by that TR, by T1 relaxation. Yes?
If you have different tissues, wouldn't they have a different MT to begin with anyways?
They might. So I'm keeping this simple, right? So I'm keeping this simple, that by definition here, right, these have, I think what you really mean to say is, wouldn't they have a different M0
Right.
to begin with? Wouldn't they have a different proton density? In general, you're absolutely right, that there's typically going to be a difference in proton density. I'm just trying to keep this as uncomplicated as possible by using an example where the proton densities are the same.
Measuring context, would have to take that into account, though.
Sure. I mean, ultimately, that would maybe we can diagram an example like that in a minute, but that would definitely weigh into the equation. But my point is here, even though that's already involved in the baseline, this difference is a function of whatever this initial baseline is, which is a function of proton density, plus whatever difference you generate by having a short enough TR to pick up those T1 differences. Okay? So in this case, we can see, first of all, let's say we place our TE at this point. So in this case, if, let's say that this is cerebrospinal fluid, and this is brain, just generic brain tissue. So at this TE, which we'll say is a relatively long TE, we have higher signal in CSF than we do in brain. So to the radiologist, that sounds like what type of an image? Right, that sounds like a T2 weighted image. So that high signal in CSF is a function of, right, waiting a long time to allow these to lose their transverse magnetization, with CSF losing that transverse magnetization much more slowly than brain tissue. Now, if we move the TE over here, what happens? Well, now, go ahead.
We'll have higher signal.
Right, we've reversed the contrast. So now the CSF is dark relative to the brain tissue. Right? This area would give you, right, more what we would call a T1 weighted image. It's not that changing the TE has anything to do with T1 contrast per se. All it's doing is removing that T2 contrast. Okay? And if you wanted to maximize similarly this contrast due to T2 differences, you would probably be better off with our first example. Right? If the TR is as long as possible, then weighting the same TE, you're going to get an even larger difference here. Your CSF will be even much brighter than brain tissue. Now, what happens if we place our TE there? Right, they look the same. So this is sort of, right, these crossing points are something you have to be aware of. So in this case, the CSF and the brain would look relatively similar. But what if instead of, CSF and brain, this were liver and tumor? So you would have just generated an image where, despite its very high spatial resolution, was unable to detect the presence of the pathology. And these things aren't always so easy to predict, especially when you're dealing with an unknown, like some type of pathology that you're looking to detect. So this is one of the reasons why when we do imaging with MR, we generate images with various different parameter settings. If all we did was put the patient in with a single type of imaging protocol, where we imaged at a single TE and a single TR, for example, well, what would happen if you ended up with this? Right? It would be a bad situation. So one of the nice things is that simply by just repeating the same exact imaging approach and changing this one parameter, we can dramatically change the contrast of the image. Okay, let's look at an example of that. Okay. So this is a series of images where a kind person laid in the magnet and allowed us to image them repeatedly over it was a pretty long period of time. And we did a whole bunch of different things. But in this example, what we've done is acquire the exact same image, changing nothing except the TE. And the echo time, measured in milliseconds, ranges here from 5, right, to 125 milliseconds. So if you think about what's going on, so first of all, this is our signal decaying over time. So as we make our TE later and later and later, one of the things you notice is that the signal amplitude is declining. So compared to 5 milliseconds and over to 125 milliseconds, there is a dramatic decrease in the overall signal in the image. So one of the things to keep in mind as you image at a longer and longer TE, yes, it does bring out that T2 contrast in the image, but it also has the consequence of leading to relatively lower signal amplitude in your images. And then if you look at the difference between, let's say, CSF and brain, where we have much higher signal in CSF at the longer echo time relative to brain, and if you look at the same area at the shortest echo time, you can see that the contrast is reversed. And maybe somewhere around 20 milliseconds or so, we might have missed it, but it's sort of blurred. That's exactly what we just looked at, right, on our graph, where we had that crossing point. So we have higher signal, right, in tissue relative to CSF at the early echo time, and we have lower signal in tissue relative to CSF at the later echo time. And at some point in here, which we may not have chosen the exact right echo time to get at, there is that crossing point. So what we can infer from this scenario of images that I've showed you is that, well, if I give you one more piece of information, which gets at what Esty was saying, which is that CSF has pretty much the highest proton density of anything in the body. So by default, we expect that if all we did was give a single 90-degree RF pulse, and we were comparing CSF and tissue, let's say brain tissue, we would expect them to start out having different proton densities and therefore start out having different amounts of signal amplitude. So at our shortest echo time, we would still expect the CSF to have higher signal than the tissue. Is that clear? So the fact that that's not the case here is telling us that what this must be is that we used a short TR and ended up with this situation as our starting point, where tissue is higher signal than CSF. And only as we wait over time, because this is losing signal more slowly, do we eventually get to the point where CSF has higher signal than tissue. Okay? So again, everything you see changing in these images is a function of differences in T2 between tissues, which become much more prominent as you get to a longer echo time. Now here's another set of images where we left everything the same except for the TR. So again, this is how often we repeat that 90-degree RF pulse. And what that means is that when we knock the spins down once, they are going to recover slowly. If we wait all the way to a long period of time where they fully recover, we knock them down again. They'll look similar to the way they did the first time around. Whereas if, on the other hand, if we wait a relatively short period of time before they fully recover, we will generate this contrast. One thing to keep in mind is that not only do we generate that contrast, but if we only let them recover part of the way, that means there's only a small amount of longitudinal magnetization that's recovered, which means that's all we have to generate signal from. So as the TR gets very short, the signal in the image gets substantially suppressed, or actually what we call saturated. So while it's true that you can use the TR to generate changes in contrast in the image, and if you look at the difference between gray and white matter in this image on the lower right and gray and white matter in this image in the upper right, they're actually inverted, right? White matter is darker than gray matter here, and it's the opposite at these shorter echo times. You may see it a little bit better over here. Similarly for the cerebrospinal fluid. But at the same time, as the TR gets shorter and shorter, you can use that to bring out T1 contrast in the image, but one of the consequences is that you'll have a significant loss of signal amplitude. Okay?